Okay, welcome to day one of Unit 1 Functions. I know for most of you it's been a very long time since you've had a math class, probably since last May. So this first unit is going to be mostly a review of algebra material. So today's lesson will focus on identifying characteristics of functions. We're going to look at our about 10 basic parent functions between what we're going to do in class, what we're going to do for classwork, and what we're going to do for homework. And then we'll even go back to some Algebra 1 ideas of simplifying exponents, knowing those rules, and factoring. You got to know how to factor. So what is a function? A function states for every input there's exactly one output. And remember function notation, we use this f of x notation where x is the input and, well, let me erase that. F of x is the output, or what we call the y value. So how does this work? Well, if we have a function and let's see, stuff goes in, stuff comes out, x goes in, and y, or f of x, comes out of the function. So what do we mean when we say by domain and range? Domain is the x values are all possible input values. My range are my y values or my f of x values, and they're all the possible output values. So besides x goes in a function and y goes out of function, we have domain goes in and range comes out, and this is all alphabetical. I comes before x, I comes before O, in and out, x comes before y, and D, domain, comes before R, range. So how can we tell if a function is either increasing, decreasing, or constant? Well, we read things left to right just like we read words left to right. So a function is increasing is if as x increases, y increases. That means something kind of looks like this. It is going uphill. A function is decreasing as x increases, y decreases. It's kind of look like this. It is going downhill. And then finally, how can we tell if a function is constant? Something is constant is if x increases, y does not change, or it basically looks horizontal. So with this next idea, when it says f of x, or what we call the y value, it says the y value is greater than 0, that's when we have the function is above the x-axis, and it says y is less than 0, that's when the function is below the x-axis. Okay, concavity is curvature. How is something curving? So anything that's linear has no concavity, has no curvature. But when we have things that look like this or like this, those are considered concave up because they are curving up, and these are considered concave down because they're curving down. So for the concave up part, these are both concave up, and the one on the left is concave up and increasing because it's going uphill left to right, and the one on the right is concave up because it is curving up, but it's also decreasing because it is going downhill from left to right. And if you think about it, you probably have heard these words before. Up like a cup. So it means it holds water. If you curve your fingers like the top two, you would actually hold something. Okay, the two graphs that are concave down, the first one on the left is concave down and decreasing because it is going downhill. And the second one is concave down, it's curving down, but it's increasing because it's going up from left to right. And you probably heard not just like up like a cup, you probably also heard down like a frown. Something like that. So when we talk about end behavior of the graph, we're talking about the far right side of the graph and the far left side of the graph. So in other words, as x goes infinity is the far right side of the graph, and as x goes to negative infinity is the far left side of the graph. So that we're trying to figure out what's happening on the far right side, on the far left side. So you've heard something called a horizontal asymptote. If one or both of the ends level off to a horizontal line, let's call this line y equals L, then that's a horizontal asymptote. That means if the farther I go right or the farther I go left, I'm going to get closer and closer to a horizontal line. Something is a vertical asymptote. Something is a vertical asymptote at x equals a. So x equals a is a vertical line. That means on the left side or the right side of that vertical line, the graph is either going up to infinity or down to infinity. A vertical asymptote means the graph doesn't just stop in the middle someplace. It means it goes all the way up or down forever, and I'll show you what I mean. So I've drawn a little grid, and I've drawn pink lines for my vertical and horizontal asymptotes, VA for vertical, HA for horizontal, and here's a graph that fits the conditions that I'm talking about. As you see, the left side of the graph, I'll take my eraser, this left side of the graph is leveling off to y equals this L, and the right side of the graph is leveling off to the right side of y equals L. And right here at x equals a, right here at x equals a, you see on one side, on this right side, this graph is going all the way up, 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 up to infinity, and on the left side of this vertical asymptote, this graph is going all the way down. It never stops, it keeps on going down to negative infinity. And then finally, when we talk about symmetry, and you've heard of the word even and odd symmetry. To me, when I hear even symmetry, I think because you could fold in half on itself, a nice little mirror, and odd symmetry is because you could spin it 180 degrees and you have the same picture. These are all things you've done before in either Algebra 1 or Algebra 2 class, and we're kind of reiterating it now, but we're going to step it up a little bit, and not so much today, but starting tomorrow we're going to use different terminology to describe all this information. Okay, so we're going to look at three basic functions. The first one is a linear function, and we're going to talk about all these characteristics, and we're going to use interval notation when it's necessary. If you remember interval notation, all real numbers means they go all the way left to all the way right. Negative infinity to infinity is all real numbers. Sometimes we use this, what I call double-lined R, for all real numbers. Quick little refresher on interval notation. Algebra 1, x is greater than 3. We do the number line. I don't know why I put down 0, but open circle, greater than is to the right. But if we want to use interval notation, it would be parentheses 3 to infinity. Okay, if we had x greater than, well, let's do less than. Less than or equal to -1, number line. It would be, here's -1, closed circle, because we're including it, less than is this way, or inequality, interval notation would be negative infinity to -1, brackets. So we're learning that a parentheses does not include that number, a closed bracket does include that number, and we always go from low number to high number, left to right. And if you wanted to do something else, let's say 4 less than x less than equal to 10 on a number line, 4 and 10, the open circle, closed circle, but it would be 4 comma 10, parentheses on the 4, bracket on the 10. And once in a while we could have something that looks like this. I'm not going to write it out in inequality notation, but maybe something on a number line that looked like this. We have two different parts of this number line, and that would be negative infinity to negative 5 bracket u for union or together with 2 to infinity parentheses on the 2 because it is an open circle. Hopefully remember your integral notation. Okay, with that said, let's go to it. Domain are the x's, and this is the easiest function. It's all real numbers. All the x's are being used. The range are the y's. Again, all the y's are being used, negative infinity to infinity. When is this function increasing? It is always going uphill, so from negative infinity to infinity it is increasing. When it's decreasing, it is never decreasing. F of x greater than 0 means when it's above, it is above. See right here, it hits the x-axis, so it is above from 0 to infinity, and when's it below? From negative infinity to 0. Concave up. Concavity is curvature. It is never concave up or concave down. Then we'll look at our end behavior. As x goes to infinity, that's our right side of the graph. As x goes to negative infinity, that's our left side of the graph. And if I look at the right side of this graph, it is going up, up, up. The y values are getting higher, higher, higher to infinity. And over here on the left side of the graph, as I go farther left, on the left side of the graph is going down to negative infinity. Asymptotes are those, hopefully those dashed lines that you see. I don't see any asymptotes on this graph, horizontal or vertical. Symmetry, well, a couple reasons. One, it is odd because I could flip it around 180 degrees, but if you look at this equation, this is x to the first power. Sounds like an odd number to me. And again, right here in the pink is my x-intercept, but it's also my y-intercept. So 0, 0 is both the x and y-intercept. Hopefully you recall all these characteristics that you did last year in Algebra 2. You know, it's not that hard. It might take a little bit to remember, but please ask questions if you do not understand. Okay, x squared, the good old parabola, the domain. All the x's are being used. There's nothing bad. It's all real numbers, but the range of the y's, I don't have any y's down below the x-axis. I only see y's up here. So the range is 0 to infinity, including 0 because it does hit right here. There at 0, 0. So I might as well put down that's my x-intercept and that's my y-intercept. Oh yeah, while we're here, x squared. This is an even function. Another reason that is even because I could fold it in half. You see I could fold this half on the other half across the y-axis. There's a nice little mirror image going on here. When's it increasing and decreasing? Well, let's see. To me, it is increasing when it's going uphill, and it's going uphill on the right half of the graph from 0 to infinity, and is decreasing because I read left to right, so it's decreasing on this part of the graph. Negative infinity to 0, the left half of the graph. When is the above the x-axis? Well, technically it is always above the x-axis, except right there at the origin. So it would be negative infinity to 0 union 0 to infinity. Because for that little moment at x equals 0, it is not above the x-axis. It is never below the x-axis. Concavity is, well, to me it is always concave up. It is never concave down. Let's look at the end behavior. My end behavior on the right side of the graph, as I go farther right, this right side is going up, up, up to infinity. And I go on the left side of the graph, see I'm going farther left. The left side of the graph is also going up, up, up to infinity. Okay, asymptotes again are those dashed lines that we see sometimes on graph. I don't see any of those dashed lines, so there are no horizontal or vertical asymptotes. Again, all this should be information that you should remember. The first two graphs were a linear function of the quadratic. You worked with those for a very, very long time. And then finally, this last equation we're going to work with is the function 1 over x. Okay, if you don't remember 1 over x, it's called a reciprocal function. It's one graph, but it's broken up into two branches. You see a left-hand branch here and a right-hand branch here. Because it's broken up into two branches, I actually have those two things we talked about before. I have a vertical asymptote at x equals 0. I have a horizontal asymptote at y equals 0. So I can even put those downs. At x equals 0 is my VA, and at y equals 0 is my HA. Therefore, I think that has some effect on domain and range. So if I look at my domain and range, my domain is not all real numbers anymore. At x equals 0, it's missing. So negative infinity to 0, union 0 to infinity. And I think the same thing is going on with the y values of the range. Y equals 0 is missing. A little sloppy right there. When is the function increasing? It is increasing when it's going uphill. Well, this branch here, look at this. Left to right, I'm going downhill, and this branch here is going downhill. So it is never increasing. Both branches, negative infinity to 0, the left branch, and 0 to infinity, the right branch, are both decreasing. When is it above the x-axis? Well, the right branch is above, and then conversely, the left branch is below. So from 0 to infinity, it is above the x-axis, and from negative infinity to 0, it is below the x-axis. When is it concave up? Well, this left branch is definitely concave down. It's curving down. In this one, even though it's decreasing, it's going downhill, it is curving up. So it is curving up from 0 to infinity, and it's curving down from negative infinity to 0. My end behavior is a little bit different. As I go farther to the right, see, as I go farther to the right, this graph is leveling off. It's getting closer and closer and closer to my function, or my y value is equal to 0. And I do the same thing on the left side. Again, this isn't going up forever or down forever. It is leveling off at y, or my f of x, is equal to 0. My symmetry, well, I can't fold it in half, but if I did spin it 180 degrees, it would be odd. And again, this is 1 over x to the first, or better yet, x to the negative 1. Either way, that is an odd exponent. And for my x-intercepts and y-intercept, right here in the middle, there's no x or y-intercept. Though I do want to talk about one other feature that isn't on here, and that is what is happening in the middle part of the graph. So maybe we dealt with this in Algebra 2 when you talked about as x approaches 0 from the right. That doesn't mean go right from 0. That means start on the right side of the graph. So I'm over here on the right side of the graph. I'm getting closer and closer and closer to x equals 0. As I get closer to x equals 0, this y value is going up to positive infinity. Do the same thing over here. It says as x approaches 0 from the left. So here's the left side of the graph. I'm over here. I'm getting closer to the middle part, or x equals 0, and this y value, or f of x, is going down to negative infinity. So those are a couple features that we're going to talk about specifically more tomorrow when we do something called limits, but it's something that you should have been made aware of in Algebra 2. Okay, this last page is really a review of Algebra 1 techniques like the rules of exponents. So when I take a power and raise it to a power, I multiply exponents. So over here I get x to the 6th, y to the 10th. That's pretty easy. When I multiply powers, I add exponents. Now it's a little bit harder when I have to add fractions. I'm not going to lie about that. I find a common denominator, 15, so I multiply this one by 5, I get 10. I multiply this one by 3, I get 12. I get b to the 22 over 15. Just leave it as an improper fraction. That is fine. When I divide powers, I subtract the exponents, so now I have to do 5/3 minus 3. Again, I need a common denominator. 5 minus 9. I get y to the negative 4/3. But if I go back to my rules of exponents, something raised to a negative exponent is 1 over something raised to a positive exponent. So I get a result of 1 over y to the 4/3. And then Over here, well, I could just multiply all these exponents. So 3 times a half times 4 over 5. And I do my canceling a little bit. I realize this becomes a 2. I get 6 over 5. I get x to the 6 over 5 as my result. Over here, I could distribute. So a raised to a power and b raised to a power raised to another power. I distribute and I multiply. So distribute basically means multiply. So when I do that, I get y to the 5/3, 8 to the 1/3. But if you recall, something raised to the 1 over power is really the nth root of that. So I have to do 8 to the 1/3 is really the cube root of 8, which is 2. And when I do all that, I get y to the 5/3 over 2 is my result. And this last one I'm going to distribute. I get to do it here, here, and here. I get 3 to the negative 2, x to the 8, y to the negative 5. And if I recall, if I have something to the negative and something to the negative, they switch sides of the fraction bar. So b to the n goes on top, a to the n goes on the bottom. If I do this here, I get x to the 8, y to the 5th, because the negative 5 goes on the top, and 3 to the negative 2 becomes 3 to the 2 on the 3 squared on the bottom. And when I clean this all up, I get x to the 8, y to the 5th over 9. Don't leave it as 3 squared, write it as 9. Okay, factoring. I'm not much of a creating of an Xbox type of guy. I will try it a little bit. I'm more of a guy who kind of use my intuition on what factors should be. But the one thing I should know is that whatever I do is that I'm always trying to multiply to get this last term, and I might trying to add to get this middle term. So if I set this up, because there's a 1 in front here, this becomes a positive 10 on top, a negative 7 on the bottom, and I realize I need to multiply and add, and I get negative 2 and negative 5, and I get x minus 2, x minus 5 as my result. Okay, it's a little bit harder when you have a 2x squared. I have to pay attention to this 2. So because of this 2, I got to multiply the first and the last, and that gives me a negative 30 on top, and this guy is still negative 7. So I need two numbers that multiply to this and add to that, and I'm going to say 3 and negative 10. Do that, and I'm going to use that, but I do have to pay attention to this negative, to this positive 2 here. So when I do that, I get 2x plus 3, 2x minus 10 by using my 3 and negative 10, but then I could reduce. I could take a 2 out of here, and I get 2x plus 3 and x minus 5 as my result. And if you check it out, it'll work because I get 2x squared, and 3 times negative 5 is negative 15, and everything else will work out in the middle. Now this last one, this one here is special. There's no middle term. It's called the difference of two squares. Okay, so I look at this and I realize, oh, this is 2x and this is 5. If you square them, and when you write it out, you get 2x plus 5 and 2x minus 5 is this very special pattern, or you could just say 2x minus 5, 2x plus 5. It doesn't matter the order that you do it in. But if you expand this out, you will realize that this guy here will give you negative 10x. This guy here will give you positive 10x, and therefore that's why there's no middle term in any of this. They cancel out. Now this last one, what you need to do is realize that, wow, there's a lot going on here. The first thing I should always look for is the greatest common factor. Do they have something in common I could take out? I could take out a 2x. What's left over when I take out a 2x? X squared minus 6x plus 9. And if you want to do your whole little X box, you get 9 and -6, and you say -3 and -3, and you get 2x, x minus 3. Another one is also x minus 3. And if you want to really clean it up, you could say 2x, x minus 3 squared is your final result.